Hi everyone, I'm Marcus Wentz from Taiko DevRel. And yeah, so there's some animations in this presentation. Hopefully they translated through the PDF, but yeah, let's get started. Yeah, so first I want to start off with PSC. So PSC is a collective of developers that are doing zero knowledge proof development. And two repositories that I want to kind of focus on for this talk are Halo2, which is the Rust Crate repository, and the ZK EVM repository that uses Halo2 circuits for ZK EVM development. Right. So what is Taiko? So Taiko is a zero knowledge rollup. So one way to think about it is like Taiko is a Japanese drum, and like with Ethereum, you have ultrasound money. So imagine like a drum kit and like a rolled up piece of paper, like a roll up, right? And before I dive into Halo 2, I want to talk about scaling in general. So there's EIP 4844, which is in the works and is planned to be added to Ethereum with the Cancun update. And I actually checked a few minutes before this talk, and there's no exact ETA yet, but it's roughly going to be Q4, I believe, of this year. So yeah, the main idea is there are going to be blobs added to the consensus layer of Ethereum, and they will expire. And I'll come back to that in a minute. But another metaphor I want to use for scaling Ethereum is like think of Ethereum as Lower Manhattan, right? So there's only so much space on Lower Manhattan, but it's very valuable land, right? So to make the most out of that land, think of the square footage as like call data and a rollup as a skyscraper that could keep going up. So going back to EIP 4844. So the magic of polynomial coefficients, we're able to, as we can see kind of down here, we're able to recover data after it expires in a sense. Like we're able to retrieve parts of the data, but we could cut part of it as well later on. And this requires a snark with a ceremony. And this was done fairly through a KZG ceremony that was done publicly. And I would say roughly about 100,000 people contributed to this ceremony, which was a huge success. So how do we have equivalence to Ethereum with Taiko? So under the hood, we're using Geth, which is the flagship Ethereum execution layer client from the Ethereum Foundation. And we also use Geth, and we're trying as much as possible not to modify the execution layer of Geth to be true to Ethereum. However, there's one thing we want to consider, that we don't want to just use Geth. We want to consider other clients, because Geth is about like 80% of the network right now. Ideally, it shouldn't be that high. Otherwise, if there's a bug in Geth, then 80% of the network will go down. So the way we address this is basically we can use theoretically any execution layer client as long as it supports ETH-get proof. One client that we're really interested in testing is Reth, which is the Rust Ethereum client being developed by Paradigm. I was actually in San Francisco last weekend at this event, and it was a blast. And I told Georgios that we're looking into this, and he was really excited to see Taiko implement this. And yeah, so we the way we get the way ETH-get proof gets the data is basically we get a Merkle tree, and as you can see here, we have not just the state root, but we also have the transaction root and the receipt root from this. And from that Merkle tree, we will actually use this for a proof relay between L1 and L2 to bridge ETH, for example. And you can check it out here on GitHub. So the way this works from a high level is we have a user submit a transaction, and it goes through the token vault and then the bridge, and then we'll have the signal communication go through here, where basically we'll have the relay submit a proof, it goes to the bridge, and then we'll unlock tokens. So that's kind of how L1 and L2 ETH is bridged between chains. So if you're new to, again, just to prepare for Halo 2, if you're new to zero knowledge proof development, I wouldn't recommend you jump into Halo 2 directly. I would recommend you start with Socrates. I have some Circom and Noir experience, but They're both good languages. I recommend Socrates because you could just open up your web browser and go to Remix IDE and then just start just like this. So here's the circuit that I took from a tutorial on YouTube and kind of brought to GitHub. So what's happening here is we have several different private fields, and then we have some public inputs, and then we hash this information, we put it in like an array, and we generate a proof to say like, hey, I know what these values will be. And yeah, you can check out this on GitHub. So now let's talk about Halo2. So actually, wait, I forgot to take this out. Yeah. Okay. So why Halo2? Halo2 is a very powerful ZK development tool. And under the hood, it uses gates. So here are some digital logic gates with their logic. And here's a very basic circuit where you just have some inputs, and then the logic is fed between gates, and you have an output linear expression that's low degree. So Halo2 also has lookup tables, and what this essentially allows you to do, it allows you to communicate with different expressions within these different columns, which I'll dive into over here. So kind of similar to Socrates, you have like the private fields, which are advice, and those regular inputs that were just public. And here for the circuit where we saw like all that hashing and the storage, that's basically the circuit, and then the selector is basically the circuit as well. So chips basically tell you what you want out of the circuit, and like basically if you, so this is from a this analogy is from this game called Mega Man Battle Network, where basically if you select, I don't know, like this type L, you can't select the other types. You have to have types that are compatible. Otherwise, you can't have that same set of features, right? So this is what a chip actually looks like with the config in Rust. So here we have these columns as shown from before, and they're being translated here. So we have some private data, some of the circuit data, and then some public data defined here. So we take that config and then we put it in a marker with the phantom data. So what is phantom data? So phantom data is just like a kind of like a dummy type where it basically, like if you don't use this field here, it'll potentially have a runtime error, and we don't want that. So we just say, hey, like we're not going to use this type like implicitly, but we want to just make sure it doesn't go out of bounds. So hence phantom data. So okay, there's supposed to be an animation here, but it's not going to play from the PDF. But basically, when you take certain chips, but you don't want to like inherently say the constraints of your circuit, you have what's called a gadget. So a gadget allows you to take these chips and then say, hey, from like a high level, hey, I want this type of application like output, right? And there's supposed to be like a little animation where it shows like the chips coming together and attacking this monster on the right. But we don't actually at Taiko use gadgets. We use the cell manager as well, and this is mainly for ergonomics, right? So think of each kind of cell as a signal, and the cell manager kind of inherently kind of separates different cells from being reused, so they're isolated from each other, kind of like how you have here. You have different signals going through different pins, and you have insulated wires. So it makes it easy to just like swap in and out between different signal communication. So here's an example of us using Halo2 to prove something. So what's happening here is this is just like a diagram showing like, hey, we have different transaction types. So we have legacy transactions, which is gas and gas limit. And then we have type 1, which is you have the access list that allows you to define transaction storage and for certain addresses, and this allows you to get cheaper gas as a byproduct of that, and also EIP 1559. So when Taiko launched, we actually just had, I believe, legacy, but not too long ago we implemented EIP 1559. It's working as expected. And we're also looking into testing RLP for EIP 4844, and this is the RLP format for that new transaction type that will have the expiring block data. So let's talk about PBS MEV with L2. So here we have searchers that are saying, hey, I want to submit a transaction to Taiko, and then we have block builders, which we have to prove, like, hey, is this like legitimate data? Like, is the RLP correct? Is all the information correct for it to be legitimate execution data on Taiko? And then what this really is from an L1 perspective, it's just another searcher, as we could see here, just a searcher with the little Taiko hat, and then it goes into the Ethereum network. And one issue that has come up that's kind of like a broader issue for ZK rollups is proving like blocks that are not provable and just being able to estimate that gas underneath that. So one way that we could get around this is by actually modifying the gas cost of certain opcodes, but we don't want to do that because that would actually not make us a type 1 ZK EVM. We want to find other alternatives, ideally. Another method is like we could just keep saying, hey, like I want to keep putting random like values and hopefully I'll hit something and then it'll go through, but that's not really efficient. We want to be precise and have accuracy from that. Another method we could try to solve this is by just forwarding unprovable blocks through like a MEV bundler. And this could work, but the caveat is that we have to trust Intel SGX, which seems pretty secure, but it's just something to consider. But ideally, we actually fully prove the block as opposed to just like forwarding it and hoping that a bundler will just accept it. So the main method I've seen so far for doing this is to, in a sense, like chunk the circuit and just break it into smaller pieces. So yeah, that kind of concludes my talk, and here are my references. Just kidding. Yep. Thank you.